Let's start with question number 31 of this series. A company runs a worker process on 3 Amazon EC2 instances. The instances are an auto-scaling group that is configured to use a simple scaling policy. The instances process messages from an Amazon simple queue service queue. Random periods of increased messages are causing a decrease in the performance of the worker process. A SysOps administrator must scale the instances to accommodate the increased number of messages. Which solution will meet these requirements? Your options are: use CloudWatch to create a metric math expression to calculate the approximate age of the oldest message in the SQS queue. Create a target tracking scaling policy for the metric math expression to modify the auto scaling group. Use CloudWatch to create a metric math expression to calculate the approximate number of messages visible in the SQS queue for each instance. Create a target tracking scaling policy for the metric math expression to modify the auto scaling group. Create an application load balancer. Attach the ALP to the auto scaling group. Create a target tracking scaling policy for the ALB request count per target metric to modify the auto scaling group. Create an application load balancer. Attach the ALB to the auto scaling group. Create a scheduled scaling policy for the auto scaling group. Now you should make use of use CloudWatch with a metric math expression for approximate age of oldest message along with a target tracking scaling policy. Approximate age of oldest message metric shows how long the oldest unprocessed message has been in the queue, and target tracking scaling automatically adjusts the number of instances in the auto scaling group based on the target value you set for the metric math expression. This ensures that your worker process can handle the fluctuating message volume. Next question. A company runs its web application on multiple Amazon EC2 instances that are part of an auto-scaling group. The company wants the auto-scaling group to scale out as soon as CPU utilization rises above 50% for the instances. How should a SysOps administrator configure the auto-scaling group to meet these requirements? Your options are: configure the auto-scaling group to scale based on events, configure the auto-scaling group to scale based on a schedule, configure the auto-scaling group to dynamically scale based on demand, configure the auto-scaling group to use predictive scaling. Now folks, the best approach would be to make use of dynamic scaling. You will use CPU utilization as a metric to trigger scaling with a criteria of utilization above 50%. Feel free to browse through the link on your screen to understand more about dynamic scaling and how you can use it in your implementation. Next question. A company hosts a web application on an Amazon EC2 instance in a production VPC. Client connections to the application are failing. A SysOps administrator inspects the VPC flow logs and finds the following entry. There is a screenshot of an entry in front of you. What is a possible cause of these failed connections? Your options are: a security group deny rule is blocking traffic on port 443. The EC2 instance is shut down. The network ACL is blocking HTTPS traffic. The VPC has no internet gateway attached. Now friends, the VPC flow log entry contains the word reject, which indicates that the traffic was explicitly denied. We can also see the presence of word ENI, which means that blockage is at elastic network interface level, and the presence of port 443 confirms it is a HTTPS traffic. Friends, just to note, security groups do not have deny rules, only allow rules. So option A is automatically ruled out. If the EC2 instance was shut down, there wouldn't be a reject log entry for that traffic, as the traffic would drop altogether. And if there was no internet gateway, traffic wouldn't even route properly again. No reject from the NACL would be seen in that case. Next question. A company has deployed an application on AWS. The application runs on a fleet of Linux Amazon EC2 instances that are in an auto-scaling group. The auto-scaling group is configured to use launch templates. The launch templates launch Amazon Elastic Block Store backed EC2 instances that use general purpose SSD EBS volumes for primary storage. A SysOps administrator needs to implement a solution to ensure that all the EC2 instances can share the same underlying files. The solution also must ensure that the data is consistent. Which solution will meet these requirements? Your options are create an Amazon Elastic file system, create a new launch template version that includes user data that mounts the EFS file system, update the auto-scaling group to use the new launch template version to cycle in newer EC2 instances and to terminate the older EC2 instances. The second option is enable multi-attach on the EBS volumes. Create a new launch template version that includes user data that mounts the EBS volume. Update the auto-scaling group to use the new template version to cycle in new EC2 instances and to terminate the older EC2 instances. Third option is create a cron job that synchronizes the data between the EBS volumes for all the EC2 instances in the auto-scaling group. Create a lifecycle hook during instance launch to configure the cron job on all the EC2 instances. Rotate out the older EC2 instances. And folks, the final option is create a new launch template version that creates an Amazon Elastic file system. Update the auto-scaling group to use the new template version to cycle in new EC2 instances and to terminate the older EC2 instances. Now, folks, you will need to make use of EFS. So you can rule out option B and C, which don't utilize EFS. Amazon EFS is a fully managed shared file system that multiple Linux EC2 instances can mount concurrently. It ensures data consistency across instances. By mounting it via user data in the launch template, you automate the setup of each instance. Auto-scaling will then replace old instances with new instances that mount the shared file system. Now, option D is incorrect as you should not create a new EFS for every instance launch. EFS should be created once and then mounted by all instances. Folks, I hope you now understand why I have chosen option A as the correct answer. But if you still have any doubts, please post them in the comment section. Let's look at question number 35 of the series. A company recently deployed an application in production. The production environment currently runs on a single Amazon EC2 instance that hosts the application's web application and a MariaDB database. Company policy states that all IT production environments must be highly available. What should a SysOps administrator do to meet these requirements? Migrate the database from the EC2 instance to an Amazon RDS for MariaDB multi-AZ DB instance. Run the application on EC2 instances that are in an auto-scaling group that extends across multiple availability zones. Place the EC2 instances behind a load balancer. Migrate the database from the EC2 instances to an Amazon RDS for MariaDB multi-AZ DB instance. Use AWS application migration service to convert the application into an AWS Lambda function. Specify the multi-AZ option for the Lambda function. Copy the database to a different EC2 instance in a different availability zone. Use AWS backup to create Amazon machine images of the application EC2 instance and the database EC2 instance. Create an AWS Lambda function that performs health checks every minute. In case of failure, configure the Lambda function to launch a new EC2 instance from the AMI that AWS backup created. And the last option is migrate the database to a different EC2 instance. Place the application EC2 instance in an auto-scaling group that extends across multiple availability zones. Create an Amazon machine image from the database EC2 instance. Use the AMI to launch a second database EC2 instance in a different availability zone. Put the second database EC2 instance in the stopped state. Use the second database EC2 instance as a standby. Now, folks, the best suited option here would be option A. Amazon RDS for MariaDB automatically provisions a standby replica in a different availability zone, handles failovers and ensures HA for the database, and EC2 autoscaling group across multiple AZs ensures that if one instance or AZ fails, other can continue serving traffic. And load balancer distributes traffic across healthy instances in different AZs, improving both availability and fault tolerance. Now folks, option B is incorrect as Lambda functions do not have a multi-AZ configuration. Option C is overly complex manual HA implementation. And option D uses a stopped EC2 instance as a standby, means no real-time data sync. Next question. A company's social media application has strict data residency requirements. The company wants to use Amazon Route 53 to route the application with DNS service. A SysOps administrator must implement a solution that routes requests to a defined list of AWS regions. The routing must be based on the user's location. Which solution will meet these requirements? Your options are configure a Route 53 latency routing policy, configure a Route 53 multi-valve answer routing policy, configure a Route 53 geolocation routing policy, configure a Route 53 IP-based routing policy. Now folks, you need to redirect users from specific countries or regions to AWS regions that comply with local data storage and handling laws. So you should make use of Route 53 geolocation routing policy. Now, latency routing policy routes traffic based on lowest network latency, that means fastest response. Multi-valve answer routing policy returns multiple IP addresses in response to DNS queries to improve availability. And IP-based routing policy is used when you want to route traffic based on the location of your users and have the IP addresses that the traffic originates from. Folks, feel free to browse through the link on your screen to understand more about the remaining types of Amazon Route 53 routing policies. Friends, if you're liking the content, do not forget to hit the like button and subscribe the channel. Let's look at question number 37. A SysOps administrator is re-architecturing an application. The SysOps administrator has moved the database from a public subnet where the database used a public endpoint into a private subnet to restrict access from the public network. After this change, an AWS Lambda function that requires read access to the database cannot connect to the database. The SysOps administrator must solve this issue without compromising security. Which solution meets these requirements? Create an AWS private link interface endpoint for the Lambda function. Connect to the database using its private endpoint. Connect the Lambda function to the database VPC. Connect to the database using its private endpoint. Attach an IAM role to the Lambda function with read permissions to the database. Move the database to a public subnet. Use security groups for secure access. Now folks, when a database is moved into a private subnet, it is no longer accessible via public IPs. If your AWS Lambda function needs to connect to it, it must be able to reach the private subnet where the database resides. And to do this securely, you configure the Lambda function to run within a VPC, specifically one that includes routing access to the subnet where the database resides, typically through private subnets and appropriate route tables. The Lambda function will then be able to connect to the database using its private IP address. Let's understand why other options are incorrect. Private link is for accessing AWS services or VPC endpoints. IAM roles control authorization, not network connectivity. And moving the database to a public subnet contradicts the goal of improved security and data protection. Question number 38. A company wants to store sensitive financial data within Amazon S3 buckets. The company has a corporate policy that does not allow public read or write access to the buckets. A SysOps administrator must create a solution to automatically remove S3 permissions that allow public read or write access. Which AWS service should the SysOps administrator use to meet these requirements in the most operationally efficient manner? Your options are AWS Security Hub, AWS Trusted Advisor, AWS Config, Amazon Inspector. Now friends, AWS Security Hub aggregates findings from multiple services like Config, GuardDuty, etc., but does not directly remediate S3 bucket policies. Now, AWS Trusted Advisor can alert on public buckets if you are on enterprise or business support, but cannot automate remediation. AWS Config continuously monitors and records your AWS resource configurations and allows you to automate the evaluation of recorded configurations against desired configurations. Now, Amazon Inspector focuses on vulnerability management and EC2 or ECR scanning, not S3 permissions or policy checks. Go through the link on your screen to understand more about the AWS config rule that will help you in this case. Next question. A company is running an application on a group of Amazon EC2 instances behind an application load balancer. The EC2 instances run across 3 availability zones. The company needs to provide the customers with a maximum of 2 static IP addresses for their applications. How should a SysOps administrator meet these requirements? Options are: add an internal network load balancer behind the application load balancer, add AWS Global Accelerator in front of the application load balancers, configure the application load balancer in only 2 availability zones, create 2 elastic IP addresses and assign them to the application load balancer. Now folks, you will need to add AWS Global Accelerator in front of the application load balancer. AWS Global Accelerator provides 2 static IP addresses that act as a fixed entry point for the application. It intelligently routes traffic to the optimal AWS region and availability zone using the AWS global network. When placed in front of an application load balancer, it meets the requirement of providing static IPs to customers and maintaining high availability and performance across multiple availability zones. Next question. A SysOps administrator wants to share a copy of a production database with a migration account. The production database is hosted on an Amazon RDS DB instance and is encrypted at rest with an AWS key management service key that has an alias of production RDS key. What must the SysOps administrator do to meet these requirements with the least administrative overhead? Take a snapshot of the RDS DB instance into the production account, amend the KMS key policy of the production RDS key KMS key to give access to the migration account's root user, share the snapshot with the migration account. Create an RDS read replica in the migration account, configure the KMS key policy to replicate the production RDS key KMS key to the migration account. Take a snapshot of the RDS DB instance in the production account, share the snapshot with the migration account, and in the migration account, create a new KMS key that has an identical alias. Use native database toolsets to export the RDS DB instance to Amazon S3. Create an S3 bucket and an S3 bucket policy for cross-account access between the production account and the migration account. Use native database toolsets to improve the database from Amazon S3 to a new RDS DB instance. Now friends, whenever an RDS DB instance is encrypted with a KMS key, sharing snapshots across accounts requires sharing the snapshot explicitly with the target account and granting the target account access to the KMS key used to encrypt the snapshot. Option B is incorrect because cross-account read replicas are not supported by RDS. Option C is incorrect as sharing alone is not enough. The migration account must have decrypt permissions on the KMS key used to encrypt the snapshot. And option D is more complex and manual, whereas question talks about achieving the requirement with least admin overhead. Let's look at question number 41 of the series. A SysOps administrator is responsible for a company's disaster recovery procedures. The company has a source Amazon S3 bucket in a production account, and it wants to replicate objects from the source to a destination S3 bucket in a non-production account. The SysOps administrator configures S3 cross-region, cross-account replication to copy the source S3 bucket to the destination S3 bucket. When the SysOps administrator attempts to access objects in the destination S3 bucket, they receive an access denied error. Which solution will resolve the problem? Your options are: ensure that the replication rule applies to all objects in the source S3 bucket and is not scoped to a single prefix. Retry the request when the S3 replication time control has elapsed. Verify that the storage class for the replicated objects did not change between the source S3 bucket and the destination S3 bucket. Modify the replication configuration to change object ownership to the destination S3 bucket owner. Now friends, by default, when you configure cross-account S3 replication, the source bucket owner remains the owner of the replicated objects even though they reside in the destination bucket. This leads to the access denied issue because the destination account does not own the replicated objects and thus lacks permission to access them even if it owns the bucket. To solve this, you must change the ownership to the destination bucket owner. Folks, as always, I have a link on the screen to supplement the reason why I have chosen option D as the correct answer. Please go through it to understand more about this scenario. So folks, that's all for this part of the series. I'll see you soon in further parts of our AWS Certified CloudOps Engineer Associate Ultimate course. Make sure to subscribe the channel and hit that bell notification icon so you are notified on when next parts in the series are released.